All right, well, the next part of logarithms that we're going to look at, the log function, we looked at using it already to solve exponential equations. But now we're going to look at evaluating logarithms and kind of looking at where this function came from or how they developed it and how it relates to exponential functions. Now, an exponential function, which hopefully you did in grade 11, is any function that's in the form y equals a to the power of x, where a is just some number. All right, now the inverse is the equation x equals a to the power of y. Now, that is something that is usually covered in this class, but we didn't have time to do it this year. But all the inverse really means is that you switch the x's and the y's. That's it in the equation. You replace the x with the y and the y with the x. So the inverse equation can be written using logarithmic form. So that's the reason we have logarithmic form is because generally we like our equations as y equals. And so in this case, there's the difference here, and I'm going to refer to this, is that here is the inverse of an exponential equation, but we're going to write it as a log, and you'll see that the base is this little number down here. The answer, if you will, is in the log, and the exponent is over on the left. That's your y value. So things are just kind of rearranged, and we'll get to that, how that works. Now, and vice versa, where the log function is the inverse of the exponential function. Now, this little number a is the base. And as I looked at, or when we looked at this morning, the log function, everything had a base of 10, but that's not always true. It's the easiest to use because it's just counting zeros, but there's obviously every other number possible. And so when you have that log button on your calculator, it is telling you that it has a base of 10. But we could have other bases. For instance, an exponential equation such as y equals 2 to the power of x is an exponential equation. And if I did a very quick table of values for y to the power, or y equals 2 to the power of x, I could put in, I'm going to start down here at 0. 2 to the power of 0, or anything to the power of 0, is 1. 2 to the power of 1 is just 2. 2 to the power of 2 is 4. You could do negative numbers as well. So if I do 2 to the power of -1, I'd get a half. And if I did -2, 2 to the power of -2 would be 1/4. Now, the reason that I'm showing you that, and I'm going to graph these actually, let's do that first. So let's graph this equation. So -2, I got 1/4. -1, I got a half. 0, I got 1. 1, I got 2. And 2, I got 4. And hopefully, again, if you've taken grade 11 math, you did exponential equations that start off rising slowly, but then take right off. So there's our y equals 2x. Now, when I look at the log function, the inverse of this, again, the base is 2. So first of all, I'm going to write it as y equals. Now, with your log function, again, we're going to have the log. The base is 2. We're going to have an x here. And what that inverse function means is that when we have our x values and our y values, when I compare it to y equals 2 to the power of x, we flip-flop everything. So x will be, first point will be 1/4, and the y value would be -2. The second point, I'd have 1/2. The y value would be -1. Instead of 0, 1, I'd have 1, 0. Instead of 1, 2, 2, 1. And 2, 4, well, 4, 2. All right, so I can plot those points. Let's see here. Is to plot my y equals log 2x button, or log 2x. All right, so we have 1/4 -2, so that's roughly right in here. 1/2 -1, I guess right in there. 1, 0, 2, 1, and then 4, 2. So there's our logarithmic function right there. sketch of it anyways. And again, when you have a log or a inverse, now this is something, again, we didn't talk about much. It's a reflection, the inverse of any function, the reflection across the line y equals x, which you can see would be roughly that green line there. All right, but again, here's what we're looking at is the logarithmic form is that up here, this is the key part today. Key part of what we're looking at is you take your base, a, goes right here. Your x, which I guess is kind of like your answer, goes right here. And then the exponent y goes over here. All right, so how are we going to do that? Let's check it out. Try some examples, of course. All right, so it says example 1, an express in logarithmic form. All right, so I'm going to write it as a log. So first of all, here we go, log. Now the base is that little number. It goes right here. The answer, I guess if you will, 49, goes right here. And that is going to equal our exponent. And again, I'm just looking back to our last class where we did the log of each function, and I was showing that that is the exponent. The answer is always the exponent on the base. When we had 10 to the power of 3, when we take the log of 1,000, the answer is 3 because the exponent on the 10 is 3. Another one here, 5 to the power of 3 is equal to 125, which again is an exponential situation, but I can again write it in logarithmic form as log. The base is 5, so a little 5 here. The answer is 125. And the exponent required on that 5 is 3. All right. If you have any questions, let me know here. Let's see, 2. It takes a little bit to get used to these logarithmic form. But again, log. The base is 2. So that's that little 2. 32 is our answer. And what exponent would I need? Is basically what this is saying. Well, I would need an exponent of 5 on that 2 to get an answer of 32. All right, now we'll go the other way, backwards. All right, so now we're going to go the other way, express it in exponential form. All right, so these are logarithmic form. Now we're going to put it in exponential form. But see that little number 2? That's my base. The answer here is 16. The exponent I would need on the 2 is a 4. So 2 to the power 4 is equal to 16. Again, just expressed in a different form. Let's see here. The next one, we got 4 is equal to log 3, 81. Well, again, our base is 3. The answer is 81. What exponent would work on the base of 3? A 4. 3 to the power of 4 equals 81. All right, let's see. One more of those. Let's see here. And then we're actually going to solve some of these. So again, there's our base of 6. The answer is 36. The exponent I would need to make that happen is a 2. 6 squared equals 36. All right, so now we're actually going to figure one out here. What we're looking for. So it says evaluate the log base 4, 16. So what is that saying? Equals, we don't know. Well, every time we had the thing on the other side of the equal sign, that's the exponent we're looking for, right? There's the 2, there's our 4. So in other words, here we're looking at, okay, we have a base of 4. The answer is 16. What is our exponent? Well, x squared or 4 squared would give you 16. 4 times 4 would give you 16. Let's try another one of those. Again, the logarithmic form here, the base is 5. We don't know the exponent, and the answer is 625. And a little trial and error. 5 times 5 is 25, times 5 is 125, times another 5 is 625. So in this case, x is equal to 4. All right, let's see here. Then C. Again, there's our base of 4. We don't know the exponent. That's what we're trying to figure out here. But the answer is 64. And so let's see here. 4 times 4 is 16. So that's 2 times another 4 is 64. So x equals 3. All right, so let's see. Let's continue on. We'll try a few more of these. Now we're going different way here. So it says solve for x. Okay. We have our base is 8. Again, the number on the other side of the equal sign is our exponent. So it looks like 8 squared is equal to x. Well, I guess x must be 64. All right, next one. Ooh, we have a decimal. So, well, we'll get to that, but we have a decimal going, or we have a fraction here. All right, so again, there's my base. There's the exponent. And the answer is a fraction. Now, when the answer is a fraction, that means our x value is going to be, our exponent, sorry, is going to be negative. And so if I try a bunch of them, negative, I'm going to try, that's a big number, 64. 2 to the power of negative 4. No, that's 1/16. 2 to the power of negative 6. Oops. Negative 6 would give me 1/64. All right. Here's one. C. Log x equals 3. Now, see how we don't have that little number? This is the log that's on your calculator. That means there's a secret little 10 there. And so we have 10 as our base. There's our exponent. And we're looking for the answer. Well, 10 to the power of 3. 10 times 10 is 100 times another 10 is 1,000. All right. Estimate the value of the following. Okay. We're not going to estimate. Let's get rid of this one. We're not doing that one. We're not estimating. We'll actually figure that out. All right. Example 6. Now, this is real. I love science, real information. That's I always try to incorporate interesting, real information when we're dealing with equations. But this is true. The Richter scale for earthquakes. I already said that. All right. The Richter scale is used for measuring the magnitude of an earthquake. The Richter scale magnitude is given by this following formula. R is equal to 0.67 log times the log of 0.37 times E plus a 1.46, where E is the energy in kilowatt hours released by the earthquake. All right. So an earthquake releases all that energy. We want to know what is the earthquake's magnitude. All right, so we're going to use our formula up here. Now, what this information is telling us is that's how much energy has been released. So that's our E value of, I don't even know what that number is, but I know it's true. All right, so I'm just going to type that in, count the zeros, if you will. All right, so I'm going to substitute into my formula. So I have R is equal to 0.67 times the log of 0.37 times that massive number we got there, 15 billion, I want to say, or trillion. Lots of energy, of course, because it's an earthquake. Count my zeros. All right, there we go. Then we have plus 1.46. All right. So now in my calculator, I'm going to find out what 0.37 times this massive number is. And then I'm going to take the log of it. So it is going to be a huge number. But the log is going to shrink it down for us. So I'm going to have 0.67 here. All right, so let's see here. I take clear. 15, 5, 0, 0. 1, 2, 3, 4, 5, 6. All right. Times 0.37. I take the log of that number, and I get 9.76. And then again, plus this 1.46. 1.46. All right. Then bedmiss, I'm just going to multiply 0.67 times 0.67 times our 9.76. And I get 6.54. And then I add 1.46. And I get, 7.999999. So it's an 8. Oh, excuse me. On the Richter scale. There we go. Now, we're going to work the other way here. How many kilowatt hours of energy would an earthquake have to release in order to be a 6.5 on the Richter scale? All right, so we have our formula up here, but this is what we're looking for this time. We want to know how much energy is required for a 6.5 on the Richter scale. So it's the E we're trying to find. All right, so I'm going to substitute into my formula up here, the R equals. So I'm going to have 6.5 is equal to that 0.67 times the log of 0.37 times the amount of energy. That's what we want to find out, plus 1.46. Okay, so I want to solve for E. Now, the first thing I'm going to do here is I can just move this 1.46 over. And so I'm going to take 6.5 minus 1.46. And so I end up with 5.04. That will be equal to 0.67, the log of 0.37 times E. All right, now, again, simplifying things. I can get rid of this 0.67 because I can divide it off. It's attached to the log function, so I can divide it off. So I'm going to divide both sides by that 0.67. All right, those 0.67s divide each other out. And so I'm going to end up with here 5.04 divided by 0.67. And I get 7.52. And again, that's going to be equal to the log of 0.37 E. All right, now here's where we're at. So I've got no more moves up until this point, no more moves normally that you would use. So here's what I'm going to do. What I can do is use the fact that this is in logarithmic form with a base of 10, because you don't see it, so that means it's a base of 10. So I am now going to convert this into exponential form. So here's my base. Here's my exponent. And the 0.37e is my answer. So I just converted it from logarithmic form to exponential form. Now, that's 10 to the power of 7.52. I type that into my calculator, and that's a massive number. I actually get, let's see here, 3311311 2.15 is the number I get there. And again, that's going to equal our 0.37 E. And let's see, can I put some commas in there at least? Get a grasp here. 33 million, okay. 113,112.15. But I want to know how much energy is released. Well, I'm going to divide both sides here by 0.37. So this 33 million number is going to get even bigger. And so the amount of energy released, because again, these 0.37s are dividing each other out, is equal to 89, count the zero there, million, I think, 494,897.7. That's a lot of energy. What are our units here? Kilowatt hours. Kilowatt hours. And there we go. So that's how much energy, and that is less than an 8, because again, more energy, bigger earthquake. And there is a ton of energy there. But again, we couldn't solve this equation unless we take it from logarithmic form and then flip it into exponential form. That's the key there.